Go ahead.
Okay. Hi, hello, good evening, everyone. Welcome to Starry Night. So, can everyone hear me?
Oh yeah, the stream's going through, so we're good. Yeah. Hooray! And we'll make sure. Can everyone hear Abby? Can everyone hear both of us? Oh yeah, the stream's going
Yeah.
through, so we're good. Yeah. Hooray! And we'll make sure. Just make sure that everyone's saying on the
Mhm.
feed that they can hear both of us. So there's two of us you should be able to hear on the feed. There's both myself and Abby. We're in two different places, so sometimes the stream. We just want to make sure the audio comes through for both people. So can everyone hear both of us? Yes, we can hear both of you. Okay, perfect. All right, go ahead, Abby. Take it away.
Okay. So, good evening, everyone. Welcome to Starry Night. We are here to walk you through the stars. So, so let's introduce our moderators. So tonight we have Zina, we have Cal, and we have Susanna from the RASC, the Royal Astronomical Society of Canada. And also, I'm your host, and we also have Matthew in here.
Hello. All right. So I also want to do since we're here, I think we might have one young special listener and viewer that's out there tonight. So in case Ida is connected tonight, we also want to say hi to Ida, maybe future scientist, engineer, or astronaut. So if Ida's out there too, let us know. Throw something into the chat. So we have a couple really cool objects to look at tonight. We're going to be cycling through globular clusters, planets, nebula, galaxies. Abby, am I missing anything? I think that covers basically everything, right?
We also have stars, double
Stars, double
stars.
stars. Yeah, we got some star systems. And at the end of the night, if we've timed this properly, we're going to have a debut of one of our most exciting winter objects. Oh, and if I lost my, I might have lost. Did I lose my feed? Oh, my feed. I think my feed crashed. My connection to the observatory. So you might have to take over for a bit, Abby, while I reconnect.
Okay, no problem. So should we go to the first target?
Oh, actually, and since I'm feeding off of me to the OBS stream, I think we might have lost the OBS stream, so I might have to reconnect. So everyone, give us 1 second because I've just lost my feed to the observatory. So give us 1 sec here. Technical glitches. It always happens. All right,
Okay.
Abby. While I'm doing this, why don't you we were chatting a little bit earlier about some of your favorite ways to observe the night sky, and you're talking about the importance of binocular viewing, which I think we sometimes take for granted. We're always thinking it has to be telescopes. So why binoculars?
Yeah, I really like using binoculars to observe the night sky because it's easier than a telescope to use. So it's always the best way to start with binoculars because if one is not even willing to pick up a binoculars, like you wouldn't really want to use a telescope. And binoculars are a great start because you can go star hopping. That's like one of the RASC observing program that I have done. So you really get to learn a lot about the night sky. You get to look at like different clusters. And we are actually going to look at a globular cluster later on through the telescope. However, it looks a little bit different from a binoculars. Instead of a lot of clear stars, it looks like a fuzzy patch, but it's interesting because that's the way you starting to learn about observing the night sky.
Awesome.
So maybe everyone of you, like if you have used the binoculars, you can share in the chat what you have looked at or what interesting things like that you have looked at or any things you like about it.
All right. Okay. I think we're almost back online here. Ta-da! Okay. Okay. I'm just gonna crop my feed back again, and then we'll be back. Sorry about that, everybody. Okay. Well, that was no good, but we got it fixed, so we're okay now. So all right, let's get back and started again. We apologize about that. Okay, so here we go. So one of the things we first wanted to start off on was two globular clusters, and these are actually my favorite objects. And as an enhancement to these, because I know we've looked at some of these before, I've been playing around with some really interesting software, and I want to show you some of the cool things that we managed to do with that software. So I'm going to restart our stack here. So just kind of reminding everyone how we do the stream from the observatory and are able to take photos is that we have a camera that's connected to the eyepiece on our observatory, where normally when we have the public come in and look, you'd be looking through the periscope and then at the night sky. But what we've done instead is we've taken a camera and we've put it on that periscope so that we're able to look into deep space and see objects. And what we're doing is we're taking 20-minute long exposures of the night sky each time in order to send it out through the camera and then to all of you. Sometimes that actually works. So what happens is we're doing each layer on top of one another. So each 20-second exposure is sandwiched onto the next one to make one bigger and bigger and bigger picture. And that's simply because as light is coming from space, it is very faint, right? These are all photons, individual particles of light that have traveled through space for thousands and thousands of years. And so by the time they reach Earth, there's not a lot of that light left. And so we need to do longer and longer exposures with the camera in order to get what we're looking at. So this is the Messier 92 globular cluster. And this one, we were having a little bit of trouble earlier with today. And Abby, you were mentioning that sky quality is not perfect today. There is some haze in the sky. And so to give you an idea, kind of, we are down here below when we're stacking our picture, you can actually see how many of the images are taken and how many are there actually stacked together by the computer. If the computer isn't able to see enough stars in the picture, then it can't actually layer the image together. So this might not be the best cluster to start off on. So I might actually flip us over back to Messier 15, which is another cluster in our galaxy, because that one actually looked, Abby and I were using that as a test earlier, and it looked amazing. So I'm actually going to flip us back to that target instead. So... okay, so right now we're on M92. M92 is also lower to the horizon, and when you're lower to the horizon, you're looking through more of what we call the soup. So it's the turbulent atmosphere. So think of it like it's a shortcut. When you're looking straight up, you're looking through a lot less air than when you're looking along the horizon. You're looking through thousands of kilometers of atmosphere or hundreds of kilometers of atmosphere versus straight up, which is only 100 kilometers, and then you're in space. So think about that. If you had a highway that just went straight up, you could drive to space in an hour. It's not that bad. Okay, let's go to M15. Here we go. And so I'll slew the telescope over. And if you're looking at the stream, you should actually see the telescope moving in real time. And this software here that we're looking at is called SkyX. If you've joined us on streams before, you know that this is this telescope software that we use to actually move the scope around and point to the sky. It's got an entire map of the celestial sphere, all programmed into the computer. And these lines here that are moving is what is the slit in the dome that's catching up with where the telescope is actually pointing, which is right here. So we should be on target now. So I'll reset our capture. And we'll start again for Messier 15. So this is another globular cluster. It's in the constellation of Pegasus. It's about 33,600 light years distant from Earth. So remember, the stars that we're looking at in this picture, the light left them over 33,000 years ago. It's one of the most densely packed clusters in the entire galaxy. And unlike Messier 92, which was the previous object we were looking at, that one is undergoing something called core collapse. So the center of Messier 92 has actually started to collapse together, and we think there could be a supermassive black hole at the center of that cluster. This one is not quite as densely packed as that one, but it's still only 175 light years in diameter. And that might seem like a long time, right? Or very quite large, because you're going to have light to travel that whole diameter. But if you think about that, there's almost 100,000 stars in this cluster, all packed onto only 175 light years. So by comparison, between us and the closest star to our own solar system is 4.5 light years, and between here and there is basically nothing. So you're talking thousands and thousands of stars all packed into one very tight space. and they're now finally starting to come into view. So I'm gonna pull up the contrast on this a little bit so we can start seeing it a bit more clearly. And there we go. All right, so yeah, we can see it a little bit more clearly, and not just stars, but we've been able to map out a couple other really interesting objects that are in Messier 15. There are 8 pulsars that are inside the cluster. Those are the dead cores of stars, usually the remnants of supernova that have exploded. And whereas some clusters, and Abby is actually going to look at after this some open clusters, which are made of very young stars, globular clusters like these are made of very, very old stars. Clusters like these are probably on the order of 11 to 12 billion years old. And so they're stars that are basically left over from the initial formation of the Milky Way. They're some of the oldest stars in our entire galaxy. And we can tell that by looking at the color of the stars, but also measuring something called their metallicity. And we kind of cheat in astronomy. In chemistry, metal is a very specific denomination of element on the periodic table. So you have metals like gold and silver. In astronomy, we consider metals anything outside of hydrogen and helium. So any other product of stars, because we know that stars take lighter elements like hydrogen and helium, smush them together inside of their cores to make all the heavier elements. And so these stars we know are very, very old because they are part of the older part of the universe when those heavier elements didn't yet exist, because stars had to die to make them and then spit them out into the rest of the universe. So that cycle creates different populations or generations of stars. The most recent generation of stars is called population 1. And those are ones like our sun belong to. Population 2 are older, and population 3 are the oldest still. They tend to be ones that have very low metallicity, so mainly just made of hydrogen and helium, and that's what we see from clusters like this one. So I'm probably going to move off of this one pretty soon so Abby can take over here. But before we do that, I'm going to show you something kind of nerdy. We've been playing around with this software. It's called Space Engine, and it's on Steam. If anyone's ever been on Steam before, you can find this software, and it basically simulates different places in space. And one of the cool things about clusters that we've talked about in the past is how, since the stars are packed together so tightly, that if you were on a planet orbiting one of the stars in the cluster, it's possible that you would never really see nighttime, because no matter what direction in the sky you looked, there'd be so many stars so close by that the sky would literally be filled with light. And one of the things we could do is kind of simulate that. So I'm going to bring up some of the pictures here that I simulated today in Space Engine, and this is kind of what that might look like. So this is standing on the surface of a planet that is inside of Messier 15, so inside of the actual globular cluster that we're looking at right now. And if you were standing on the surface of one of these stars or one of these planets, that's what nighttime might actually look like on one of these planets. This is a planet with little atmosphere, and this is kind of an example of what one of those planets might look like with atmosphere. So this is nighttime on a planet that looking up inside of a star cluster. And especially if you look down here along the horizon, it's like looking at 1,000 sunsets all at once, kind of like pouring over the horizon. So that might be something that you could see. Cooper says here, ultimate light pollution. And that's true, because it might actually be difficult to study the wider universe. If you were on a planet inside of one of these clusters, you might not know that there even is a wider universe out there, because it would be too difficult to see outside of the cluster because it's just so bright. So one of the interesting freaks of nature is that we happen to be where we are in a place where we do get a better view of the wider universe. Otherwise, we just not might be able to do that. All right, so that's it for the 2 globular clusters. Abby, I'll let you take over and we can jump into some of the open clusters.
Yeah, sure. So we're now going to look at an open cluster. So this is a little bit different from a globular cluster. So this is the software SkyX, where we use to locate different objects, and you can see that there's a brown line on it. So that's how the slit of our observatory. Yeah.
Those colors are so pretty. I like that you can so clearly see the distinction between like the newer stars and the younger stars, like the red and the blue in there. Whereas by comparison, the globular cluster is is mainly just old stars, which is why the color from them typically tends to be so much redder. Whereas in an open cluster like this is 37, right, Abby, that we're on right now?
Okay, so
So Abby, we're on Messier 37 right now, right?
Yeah, so we
Okay.
have M37 in here.
Yeah, and we were just saying earlier, I was mentioning the fact that like I think I might have had you might have not been able to hear me for one second. I'm having issues with my headset mic. So Abby and I are talking on two different microphones while I'm talking to you on a second microphone because that's what our setup is in the era of COVID and trying to do this. But I was mentioning Abby, you probably didn't hear me, but I was saying that unlike the globular cluster where all the stars are so clearly red because the cluster is so old, the open cluster has this nice diversity of the color between them, between the blue stars and the red stars.
yeah. So here we are. So this is the M37 open cluster. So this is the one of the open cluster located in the Auriga constellation. So we have totally 3 different open clusters in Auriga, and this is one of the most compact open cluster in the constellation Auriga. So as we said, like it's an open cluster, it's a little bit different from a globular cluster. However, this is like one of the more compact version of an open cluster. So if you're looking into binoculars, it will look very compact as if it's a globular cluster, but only the difference is that it looks as a like more irregular shape rather than a round shape. So in this open cluster, we have around 2,000 stars in here, and there are a lot of red giants. As you can see, like there are some red stars in this open cluster. And one of the difference about open cluster is that open cluster, they locate like on the opposite side of the galactic core. So they're mostly on the arm, they're younger, unlike globular cluster, which are older and located in the core of the galaxy. Yeah, so I remember like looking at open clusters with my binoculars, and it's quite interesting. Like I haven't looked at M37 myself, but I have looked at another open cluster like for the summer. It's also another super compact cluster, and it took me so long to look for it because I I was still learning how to recognize an open cluster. So like it was hard, but eventually I found it. So that was the Delta cluster. It's also another super compact open cluster.
Awesome. There was a question. I don't know if you saw it, Abby, in the stream. Since we were talking, just this is a bit of a tangent about binocular viewing, but someone was asking whether or not you can see nebula well in binoculars. How do you find nebula view for binoculars?
Oh, um, for me, I think it actually depends on your location because I mostly done my binoculars observation on SFU Burnaby, and since there are a little bit of like pollution, so some of the nebula can be really hard, but most of the prominence one are easier. So for example, we're gonna look at later on the Orion Nebula, the M8 Lagoon Nebula are easy enough, but however, there are other fainter ones are kind of like just hard to look at
Hmm.
unless if you have a nebula filter for your telescope or your binoculars, that might be easier.
Okay, cool.
Yeah.
All right.
So should we move on to the next cluster?
Yeah. I was like, one of the things that was interesting about this and was that this cluster is kind of like opposite the direction of the other ones we were just looking at. So whereas the globular clusters kind of float, this is another thing about globular clusters, just kind of going back to them for 1 second, is they kind of float in a halo of blobs all around the center of the galaxy. It was actually one of the ways that we helped to map out how the galaxy looks. Like the shape of the center of the galaxy is because the globular clusters were a way to kind of see like milestones or kind of marker points around the galaxy to map them out. Whereas this cluster is kind of opposite of us from the direction of the center of the galaxy. So it's kind of neat that by looking at some of these structures and these objects that we can actually figure out where we are relative to everything else in space. It's imagine to think that we are literally stardust that can now look up into space and study other stardust and figure out where we came from. That's kind of profound when you think about it. Do you imagine, Abby, that inside of one of these open clusters where these new stars are forming, that maybe that someday someone will look back at us and see our star? That could be a thing, I think.
Oh yeah, I did think about that sometimes. Like it might be spooky to think about it.
Yeah, you
And
know.
also echoing to earlier what you mentioned about on the opposite side of the galaxy. So our Earth revolves around the sun. So during summertime, we're facing the galactic core. So that's why you might see a lot of great pictures of the Milky Way galaxy during the spring or summertime.
Hmm.
However, like as we're approaching the fall and the winter time, we're actually looking outside of the galaxy. We're looking towards the arm and towards a different direction. So that's why we'll be also looking at different star clusters, and also we are looking at different parts of the Milky Way galaxy. So most of the astrophotography for Milky Way during the winter time shows up a little bit different. You can see like it's usually just a really faint silvery bluish arm. So we are only looking at the arm of the galaxy instead of the core like we have in the summertime.
Yeah, that's awesome. Yeah, and I guess, and I was thinking about like the best way when people would sometimes ask us at the observatory, I had to explain like our position in the galaxy, and I try to tell people it's like, it's like we kind of live in the Burnaby of the galaxy. We're out in the suburbs. We're not really like right in the downtown in the core of the galaxy, like that you can see with those beautiful pictures of the Milky Way that you're seeing. When you're like looking into the core, you're basically looking into the downtown, of the Milky Way galaxy, which where apparently it might not actually safe for us to be, right? Because we're thinking that, there's where we have a habitable zone around our star, our own sun, where it's healthy for our planet Earth to be, where it's not too hot and not too cold. There's some theories that suggest that galaxies themselves might have habitable zones where if your star that you're orbiting around is too close to the middle, where you might get too exposed to radiation from exploding old stars, or get maybe even blasted by when the black hole burps at the center of your galaxy. That might all be bad things. So again, yay us for being where we are.
Yeah, so here we are. So this is another open cluster. So as you can see, it's not as dense as the last one we have seen. So this is the M103 open cluster. It is located in the Cassiopeia constellation. So Cassiopeia is quite of a more special constellation because it's a circumpolar constellation. So that means that you might be able to see it most of the time throughout the year. So this open cluster locates 8,000 light years away from the Earth and is 16 light years across. So that means it takes 16 years for the light to travel from this point to the other point. So this cluster, it's kind of special because there's this star, a very bright star in here. But actually, this star, it's called Struve 131. This star dominates the overall brightness of the cluster. But however, this star is not part of the cluster, so meaning that this star is not gravitationally bounded with the other stars. Instead, this star it's only a foreground star that happens to overlap with the open cluster. So this star is at the magnitude of 7, and most of the other stars in the cluster it's at the magnitude 10. So that's why it dominates the overall brightness. So if you're looking at this cluster with a binoculars, it shows up as a wedge shape or like a slice of orange, if you like to say.
Nice.
So you can see like there are a variety of stars in this cluster, and there's this red star in the middle. So this star is actually the brightest star in the cluster, and this is the red giant. So the red giant star is like the older stars, like I would like to call, like they're at their ending of their life, and they're rather big, and they're usually very cool and bright.
Yeah, and my understanding is that in open clusters like this, because some of the stars can be quite large, especially like the ones like blue giants and things that form in these clusters, that they might, they might explode just on the order of a few million years before ever having a chance to, have anywhere near the length of a life that like a star like ours might have, and therefore might not be the best places to live. If you were on a planet surrounding one of those stars, so it's interesting that like those stars might be born, live, and die while some of the other like stars in the cluster is still forming. So it's amazing when you think about that. My understanding is that some of the explosion around those stars actually helps to trigger more star formation inside of those clusters too, which is kind of neat. So you have a whole cycle like birth, life, and death all going on pretty rapidly.
That's so cool.
Yeah, isn't it cool? I think that's super
Yeah,
cool.
it's cool. And
Yeah,
this is
and
beautiful.
whereas like the stars in the globular cluster can be, they're billions of years old, but sometimes these stars are just on the order of millions and they're already gone.
Yeah, that's right. It's cool. And so let's move on to the next Messier.
This Messier one is funny.
Yeah, because when you think of Messier, like you might think of it as a galaxy or a nebula or a star cluster, but however, this one is a different catalog. Yeah. So someone might ask why the name Messier. So actually, Messier is the name of a French astronomer. So Charles Messier, he is very interested in hunting for comets. So actually, he's not interested in looking into nebula, galaxies, or star clusters. So one thing about looking at comets, because during that time, like they don't have really super advanced technology or telescopes. So what they're looking at, it's like it usually like when they are looking at the galaxies, it usually shows up as a fuzzy patch, like you're looking in a binoculars. So it's very easy to confuse that with a comet. Like if some of you have looked at the comet Neowise earlier in the summer with a binoculars, it looks like a fuzzy patch when you're looking into a binoculars or a telescope. So that's why he cataloged a lot of these objects down that are not comets, and that's something that he wouldn't revisit for his further research on comets.
It's kind of neat to think that you have a person who basically spent their whole life looking for one thing and created an entire catalog of objects that's not that thing, that we all now just use to basically be one of the main things that we use to like follow the night sky or to check out the night sky. So like here's Charles Messier being like, I'm gonna make an entire catalog of comets, and then made an entire catalog of not comets, but ended up being one of the most famous list of objects that we have in the night sky. I think there's some kind of life lesson in there somewhere. Persistence, I don't know, future hope of or worth of your work, even though it didn't turn out the way you thought it was going to. I think so.
Yeah. I kind of think of it as like work hard. You never know if you're gonna contribute or help someone else like one day.
Yeah, exactly. Yeah. Yeah, Susanna mentioned that here too. She says the definition of irony. Charles Messier is famous for the catalog of fuzzy objects he found, not the 13 comets he actually found when he was going to look for comets.
Yeah. So, yeah, here we are. So, as we mentioned, like the sky condition might not be very great tonight, so it might show up a little bit fuzzy. So here we are. So this is the M40. It's also known as Wernicke 4. So Wernicke is another. It's a very small catalog of double stars. So there are only 7 of them, and this is the number 4. So this is a double star located in Ursa Major, the Big Bear constellation. So what happens back then is that this is believed to be an error cataloged by Messier. When he was like cataloging down like all of the objects that he's not interested, he wrote down that there's a nebula in here. However, when another astronomer go back to refer to the same location, there was no nebula reported. Instead, it's a double star. So a lot of people believe like it's one of the mistake made by Messier.
It's awesome. So it's like a Messier. It's sort of a one-off to just have
Yeah.
like this weird double star system. Yeah, that makes sense. Yeah.
So, well, actually, this is a double star. It's only an optical double star, so meaning that the 2 of the stars, they're not gravitationally bounded to each other. They happen just kind of overlap in a very similar location, looking like as if they are in the same pair.
Cool. Yeah, and there is like a distinct. It looks like there's a distinct color between these two. Is that right, Abby?
Well, as I remember, like have very similar magnitude, and they should be the same star. They are all type B star.
Oh, okay, cool.
Yeah.
Right.
So they are blue stars.
Blue stars. How would a type B star compare to say our star? What would be if someone was like, hey, what's our star compared to say one of these that we're looking at right now? How would it be different?
So the main difference is that like, well, how it looks like, the color, the temperature, because there's this diagram that astronomers use to classify different stars. So that's the Hertzsprung-Russell diagram. So there are like different variables in it. There's the luminosity, there's temperature. So our star is kind of like in the middle of the diagram. We are type G, we're a yellow star on the main sequence. And type B stars are blue stars. They are hotter and they are more luminous.
Cool. All right. Okay. Now, you had mentioned that this is an optical binary, so these stars are not actually in a system with one another, but we do have one coming up next. Shall we move on to that one?
Yeah, sure. I'm looking
Okay.
forward to it.
Yeah, okay. So this next star that we have coming up is an actual bound star system, multi-star system. So rather than, we've got, like Abby was saying, that there's some star systems that are called optical systems or optical binaries, where it looks like the 2 stars are close to one another such that they might be an actual binary star system, but one of them could actually be really far away from the other one. It's just from our perspective that they look like they're close together, but they have no actual relationship with one another. They're not bound by gravity. Whereas this system that we're about to look at, which is called Almac, definitely is all bound together, and there's more than just 2 stars in the system, and we'll show you. So let's move to that one next. All right, here we go. And Almac is in the constellation of Andromeda. And it's almost straight up above us. So it'd be interesting. This will be a neat slew for the telescope. If you're watching the telescope video, it's going to basically almost point straight up.
Wow.
And probably should turn, yeah, it'll also turn and spin around because it's trying to reach right up into the sky. The dome's going to spin all the way around to try to get to it. Which is pretty cool. And if I I don't know if this will, I've never tried this before. If my mouse will actually, if I'm looking at different windows, I should be able to point to the observatory where, I don't know if you can actually see this or not, but I don't know if you can actually see my mouse over this window. I think you can. But right down here, this is actually where the camera that you're looking through is connected right there. So when you're looking at the periscope that's coming down off the telescope, and you can see just faintly, you can see a cable near the bottom of it. That's where we all are kind of together with the observatory. We're all connected to this thing that's hanging off the, which is normally the eyepiece here, connected to the right side of the telescope. So for those of you who have actually been to the observatory, you know that you've come in through here and you're actually like seated down. And then we all kind of like hang out there looking at together through the eyepiece at the observatory. So I don't know if my mouse actually showed up on that window or not, but yeah, anyway, so that's normally what we're all sitting down and looking through, but that's where we've attached our camera now. Okay, so let's take a look at Almac. So we're going to clear this view, and these two stars should show up pretty brightly with one another if we're on target. Oh, yeah, that's nice. I might actually switch to a lower exposure, though that is quite pretty to look at.
Wow.
That's pretty neat. You can definitely see like these spikes. In case anyone's wondering, when you actually take a photo of a star and you see these spikes that come off a star like that, they're known as diffraction spikes, and that is actually light that's reflecting off the internal structure of the telescope itself. So certain types of telescopes will create that pattern on starlight when a picture is taken of it. So if you ever wondered what that pattern is off a star, that's what it actually is. These are called diffraction spikes, and it's basically an optical artifact that's created by the telescope. Now it's hard to tell right now because we're doing a longer exposure on this star, and I might switch back to a different mode so we're not doing such a long exposure, but you could just barely make out that there's a little bit of a blue blob to the right side of the star, and that's the second one that's in the system. So I'm going to experiment here a little bit. I'm going to switch modes on our camera and turn off the long exposure mode and turn off our live stack view. Here we go. Okay, so rather than stacking now, what we're basically doing is just taking we're basically taking a video. So you're almost kind of looking now at a live video instead of stacked images through the eyepiece. And so you can see the two stars here. I'm going to zoom in on them a little bit more so we can see them a bit more clearly. Let's see. Let's try 125. There we go. There you go. So the reason why they're bouncing around like that is because we're literally looking at a video through the eyepiece, and you're seeing the motion of air in the atmosphere. And so when we look up at nighttime and you're seeing a star twinkling in the air, one of the things that astronauts mention when they're out in space is that stars don't actually twinkle in space. That twinkling effect is entirely because of the atmosphere causing the light to bounce around. So what you're seeing is the twinkling is the actual motion of the stars. Now, a couple weeks ago when we've been doing streams, we were using, when we wanted sort of like a double cluster, a binary pair of stars to look at, we were using Albireo as another one that we've used in the past. And you have this striking distinction between one of the red stars and one of the blue stars. But kind of a disappointing thing about Albireo is that it turns out, although this was kind of a point of scientific contention for a while, it turns out Albireo probably isn't actually also a real gravitationally bound star cluster. It's just a visual binary, whereas this set of stars is. However, it isn't just two stars, it's actually four, which is kind of neat because the one on the bottom, and let's change our exposure time per frame so we get these a little bit brighter here. There we go. The blue star on the bottom is actually three stars. It's a triple star system, and whereas the red star is one on its own. And so you actually have a quadruple star system altogether. The fancy spacey name of this star, while it's called Almac, its actual space designation is called Gamma Andromedae because it is part of the Andromeda star constellation. So again, the blue is a triple star, and then the red is one orange giant. So you have 3 blue stars and then 1 orange giant. That's part of the system. Almac, in its traditional name, it's the name comes from Arabic. A lot of stars actually, the names come from Arabic, and the actual name in Arabic means desert lynx. So this is the desert lynx star. And in Chinese, though, that this star's name translates to the first star of heaven's great general. So just kind of a note there to point out is that our night sky, in a way, is primarily dominated by sort of the Greek-Roman traditions, but there are many other traditions through thousands of years in other civilizations and other languages that had all different names and different constellations for the sky. And I think that's one really cool thing about astronomy, because that means that people throughout history were all looking up at the same stars, giving them all different names, but we all saw that sky together. And so if there's one thing that really kind of binds all civilizations on our planet together, it is astronomy, which is kind of neat. So one of the things I was interested in is I wanted to know, okay, how does a quadruple star system actually, like, what are the dynamics of that? So there's a picture here that I got, and it shows how all the stars actually move around one another. And this is it. So this is how the stars actually move in the system. So you have the one orange star, which is that is orbiting in a common center of mass, which is here in the middle between the whole system. And then you have the other stars. So you have the one blue star, and then it's 2 other tinier, one kind of yellow and one orangey star that are kind of orbiting each other. And then this whole system orbits, and then the whole thing turns around all in a circle. So to give you an idea of what the orbital periods of each one of them are, these 2 stars orbit each other about every 2.67 days is their orbital period. So imagine 2 giant stars just spinning around each other once every like 3 days. Then this system, between C and then BA and BB, so B alpha, B beta, this star in its own little mini star system is orbiting each other once every 67 days. 64 years, once every 64 years. And then these 2 stars, or this one cluster, and then this other star, they orbit again all one another in this entire circle once every 5,000 years. So you have a couple days, a few years, and then thousands of years. This system all in one big giant dynamic, all moving around one another, which is pretty awesome. So, going back to what Abby was saying about Messier, 40, you have 2 stars that actually aren't interacting with one another. And then by contrast, you have Gamma Andromedae here, who, there's this giant interaction or dance between all these stars in the sky. Now, the question is, how do we know that? Right? Because when you're looking at these stars through the eyepiece right now in the telescope, it's almost impossible to make any distinction at all, especially you have the 2 stars, but to see the other 2 that are a part of this, the blue star system here, is really tough. So the way that that's done is actually through a process called spectroscopy. And so we don't look at it visually through telescopes. We're actually taking the light itself and splitting it apart through prisms. The light gives us an indication that it's coming from individual different sources. And so we can actually take the light and split it apart and realize, oh, that light is actually mixed together from 3 different stars that all have 3 independent compositions and different types of brightness. And we actually have a spectrograph at the observatory, and we've used it for a couple different really cool projects. But we would be able to do something very similar to that with our own telescope and using the spectrometer over at the observatory. And we've done similar projects on it too before. So
that's really cool.
I think that brings us to the end of stars, because we've been primarily just looking at stars, star clusters, globular clusters, open clusters, binary pairs, and star systems. So I think we're going to take a look now at some nebula. So Abby, do you wanna take over?
Yeah, sure. So we're now going to look at a nebula.
moving so far from the previous point. And sometimes the dome has so much farther to go than the telescope. They move so much more quickly. It's coming. This is a common thing that happens as well when we're looking through the telescope and we're like, did something break? And then we realize, no, it's because we're looking at the wall of the dome. And you're like, oh, okay, wait a second.
Yeah.
It was fine. When you're looking at the telescope move, as you've probably seen from the tiny videos on the corner there on the display, when it shows the dome and the telescope moving, it's clear to see that the dome does move so much more slowly than the telescope. The telescope can actually, when we looked at the technical specifications of it, it can actually spin around at 360 degrees in 2 seconds. So it moves really fast. It's on a magnetically driven motor system. And cool thing right now that's going on, I don't know if Lawrence is in right now, but we're working with another scientist on a project. His name's Lawrence, and they're doing a project to try to track the International Space Station using our observatory, which is really cool. So we haven't used SkyX, the software that we're using to point the telescope, can be used to track orbiting objects. And so in addition to the entire night sky being programmed into the system, it also has in real time the position and motion of all the satellites that are in the sky as well. And so it's possible for us to load up the position or path of the satellites, click on them, and actually have the telescope try to follow them. Now, so far, while theoretically this is possible, our initial attempts to do so have not completely worked out yet. We actually have buried somewhere in some old data, and I should go and find this one day. But we do have an image of the International Space Station that we took with the telescope. It doesn't look nearly as good as images of the ISS that people have probably seen, where it's superimposed over things like the moon or the sun. It's just basically this big blur, but the blur is in the shape of the space station, and I thought that was pretty good for us, given what we could do. So, but yeah, we're trying to expand on the telescope's ability right now to track moving objects, and it's part of an overall larger project to create algorithms for satellites that are imaging the Earth, so space-based satellites that are imaging surface targets on our planet, to rotate counter to their motion across the planet to actually slow down the rate at which the camera is seeing the Earth. Because right now, if the camera is in a fixed position and it's moving over the Earth's surface really quickly, it doesn't have a lot of time to really absorb a lot of light from the ground, and so the images tend to be more fuzzy. But if the satellite can move counter to the ground, then we're able to take more photos that way. How are we doing with the telescope, Abby? Is we having some issues, or?
Yeah, it seems like it's not stacking.
Oh.
Just trying to checking.
Yeah, we've got two stacked images and 2 ignored. Are we on Dumbbell? Is that where we're on right now?
Yes, we're on Dumbbell.
Okay.
Maybe you want to take over control as I'm introducing Dumbbell?
Yeah, sure. Do you want me to see if I can? First of all, are we pointed in the right direction? I noticed there was an error from the dome earlier. I just don't know if we're actually pointed the right way. Let's see. Okay. I'm just looking at some of our cameras here. Oh, we're pointed through a hole, so that's a good sign.
Yeah. Okay.
Okay, so we are aligned on the object, so that's good.
Okay. I see a question in the chat. Okay, so like the star Almac does not have a Messier number because it's not an object that's kind of like discovered by Charles Messier.
Yeah, that's a great question. Yeah, because
Yeah.
Messier was really, as Susanna was saying earlier, he was kind of looking for fuzzy stuff, whereas the stars like Almac and stuff were not fuzzy, and especially to older telescopes when we didn't have the ability to make the distinction, we didn't know that they were multi-star systems, right? So.
Yeah, because like one fun thing about telescope, like it's usually not about the magnification, but it's about the resolving power. So older telescope, we do not have as much technology. We do not have large mirrors, so it has a lower resolving power. So as technology is advancing, we have better telescope. It's easier to resolve like some stars. So for example, like Almac, when you're looking at it, it might look like just like a one star. But if you are using telescope, it has a better resolving power, so you can see more star system.
Cool. I think your nebula is starting to come into view.
Oh, that's great.
Yeah.
Yeah, it's like coming into view.
So as Abby was pointing out a little bit earlier tonight, the sky conditions are pretty clear, but there is a bit of haze in the sky. And as Nikki here is mentioning in the chat, M27 is pretty low in the sky right now. So that also means that we're looking at a lot more of the soup and junk to see nebula. And whereas nebula are pretty faint, so we're always going to be a little bit challenged more. But here it's starting to come through, and it looks like we're starting to get some frame stacks through the camera, which is great. So we had 4 ignored frames, but now we have 7 that have been added to the stack. So we might have actually been looking at a bit of haze that moved out of the way, which is good too.
Yeah, okay. So here we are. It's not like normally it might be more clear, but yeah, so you say like there's some haze in the sky. It's close to the atmosphere. But so now we're looking at the Dumbbell Nebula. And the Dumbbell Nebula, it's 1,200 light years away from the Earth. And this is also another object that's discovered by Charles Messier. And so something special about this nebula, is that this is the first planetary nebula discovered by Charles Messier. And as you can see, like because like it has a shape of a dumbbell, so it's named as Dumbbell Nebula. And also there's another unofficial name. I remember in the previous section, someone mentioned that it looks like an apple core. And yes, apple core is another unofficial name of this nebula. So as you can see, like there are several colors in this nebula, and they represent the different type of gas the star is emitting. So the green color, it's indicating that it's hydrogen, and the blue color indicates oxygen, and the red color indicates nitrogen and sulfur.
The cool thing about these too is because some of these nebula are expanding quickly enough, and I don't know off the top of my head. Maybe someone in chat would know, but some of these I don't know if what planetary nebula. I know that there are some supernova remnants which do expand even more quickly than planetary nebula, but it's possible from year to year to actually see the change and growth and of the shape and structure of the nebula, which is amazing. It's one of those things where like, you know, you think it's static, but then you're like, no, it's actually changing over time scales that even humans can see them, you know, which we think is pretty difficult considering the age of the universe and how quickly they change. Nikki mentioned that crab is one of them, which might be the next thing on our list, so we might get to see that one. So that's pretty good. There you go.
Yeah. Yeah, so this is a Dumbbell Nebula. Yeah, personally, I find this nebula like so beautiful. I really like the shape and the color of this nebula.
So fun story. This is I'll tell you this one. So this was back in 2000 and I think 13 or 14, and I had just met Howard Trottier. And the reason how that worked out, or how I met Howard, was because I was down picking up a telescope at a store which is unfortunately now closed, Vancouver Telescope. It's reopened now. One of the staff members that worked at Vancouver Telescope has reopened on Kingsway. It's called Markarian Fine Optics. It's run by a guy named Harut. Harut's the bomb. So by the way, if you're looking for telescope equipment, go talk to Harut because he's amazing. He helped me pick out my first telescope. Anyways, since I was there at the store and getting a telescope, they said, well, obviously, if you live and work up at SFU, you must know Howard Trottier. And I was like, no, I don't. I haven't talked to Howard. And they were like, what? You got to talk to Howard. So, I sent Howard an email. And anyone who knows if anyone knows Howard, he's often like has his hands in a million different projects. And so I didn't hear back from him right away. So I was like, you know what I'm going to do? I'm finally just going to go sit in one of his lectures and hang out with him. And, and I went and introduced myself afterwards. And he's like, here, you're that guy who's been sending me emails. I'm sorry I didn't get back to you. Or my best Howard impression would be like, oh, you're that guy that was sending me emails. I got to get back to you. But he told me, he's like, hey, in a couple nights from now, I'm going to be setting up my own telescope and we're going to do photos. I was planning on doing photos of the Dumbbell Nebula. Why don't you come and hang out with me? And I was like, okay. And we set up in the spot where the observatory now is, because it hadn't even been constructed yet. So we were hanging out in this field with Howard's little personal telescope, going out and taking photos of the dumbbell. And that was the first time I ever sat down to do any long exposure photography through a telescope. And I had the privilege of being able to hang out with Howard Trottier on the future site of the Trottier Observatory and taking pictures of the dumbbell. And then on my way home, I ran into a very large bear, but he was more interested in garbage, so it was fine. That's why I'm still here to tell the tale.
Wow, that's an interesting story. Yeah. Well, speaking of nebula, what's your favorite nebula, Matt?
Oh, wow, that's a good question. You know what? My favorite nebula is going to be the one that we're going to see at the end of this show. That'll be the one that's going to be the favorite.
Okay,
Yeah.
great. Oh, everyone, you can put down in the chat, what's your favorite nebula?
Yeah, if you got a favorite nebula, let us know. Because we also need other targets to look at from night to night, too. So if you got a
Yeah.
favorite thing that you want to see, then, we can put it out there. How many were...
Yeah, for me, I think my favorite nebula would be the Helix Nebula because like it's super beautiful. It's also another planetary nebula.
Let's see if we can bring out a little bit more. Let's see. Hang on.
Oh yeah, I saw a question in the chat. Is it easy to find it in binoculars? Personally, I have tried looking for the Dumbbell Nebula with binoculars, but I failed in finding it. But I believe if there are some more powerful binoculars, yes, you're able to see it in your binoculars. And we're having some very interesting answer in here. We have the Dumbbell Nebula, we have the Running Chicken Nebula, and we have the Horsehead Nebula. Yeah, I like the Horsehead Nebula. It's a dark nebula and it's beautiful.
Yeah, those are things that definitely will come up more, toward the winter time as well. This image normally, I think dumbbell. I think we've got it maybe to look a little bit clearer in the past, but it looks like some of the frames are being ignored again. So when that happens, basically when we're stacking, the reason why we stack frames is to increase something called our signal to noise ratio. So you got a lot of noise that comes in on just one exposure, but as you're adding them in, basically what happens is because the photos that are coming from the object, so the stars and the nebula itself, are relatively always the same, but noise is randomized. The computer knows that from frame to frame, the pixels that are jumping around are really just noise, and so they start getting subtracted out, and your picture becomes clearer. But if we're having frames that are being chucked, and that could be because of maybe some of the scene conditions lower in the horizon, then we start getting more noise, and so you are seeing some noise in this picture, and that's primarily why. But yeah, you can still see it there. Cool. Anything else you wanted to share about dumbbell, Abby?
Yeah, I think maybe like that's pretty much about
Okay.
like what I have to share. Yeah,
Cool.
it's just a really beautiful nebula.
It is very beautiful. Yeah, and I think we do have a lot of data from dumbbell off the telescope's primary camera. And I think at some point we need to go in and play around with that a little bit more. I'm going to try to stretch this a wee bit. I feel like we can get more color out of this. Let me try one more time.
Yeah.
But I think we're just struggling with data this low to the horizon.
Oh, and we have a lot of answers coming in. So other than the Horsehead, the Orion, we also have the Pelican Nebula. And we also have the North American Nebula and Phoenix Nebula.
Yeah, and some of them, like, so Abby, what was our success with North American Nebula the other day? Because we actually tried that one.
Well, yeah, we actually tried testing out the North American Nebula. However, our telescope are able to pick up the colors, but since like the North American Nebula, it's a little bit large and a little bit wide, so it's wider than the field of view of our telescope. So it ends up only as a pink patch and some star clusters.
Yeah.
So, yeah.
Yeah, that's unfortunate. So some of the nebula, their surface, we call it the surface brightness, but they might be bright as an object, but because the brightness is spread out over such a large area, it's actually difficult even for our little camera that we use for public streams to pick up. It might be one of those things, especially like North America, where we might be able to pick it up with our primary camera, doing like long exposures for a couple hours, but in a few minutes, that might be a little bit trickier to do. Yeah, actually, Cynthia asked, why is it called a planetary nebula? And that's a good question. Abby, do you know why? Why are planetary nebulae so called? What is that? Where does that come from?
Oh, actually, like the name Planetary Nebula is it doesn't really represent what it actually is because it has nothing to do with planets. It only kind of looks like a planet because it has a round disk.
Mm-hmm.
So what happens to planetary nebula is that they are kind of like the dead version of a medium like size star. So just like our sun. So when our sun dies, like it will spread itself into a planetary nebula as well. So another example of the planetary nebula is the Ring Nebula that we have seen earlier in
Mm-hmm.
the season. That is a gem. I really like the colorful color of the Ring Nebula.
Yeah, totally. Yeah, and so a lot of the reasons why the word planetary comes from is that people thought it might be the formation of a solar system, or in the past, people thought it might have been a planet that they were looking at. So kind of the name sort of stuck. So in a way, it's planetary nebula is kind of a misnomer because there's nothing really planetary about them really at all. I mean, there might be planets in there somewhere that are part of now a dead solar system, but yeah, there's nothing really planety about these. Okay, so moving on, we're going to go to a different type of nebula now, whereas this one was a planetary nebula. So this is like a slowly dying star. Stars that are lower mass like ours will have a fate like this. So it's possible that if someone might be doing a Starry Nights on another world 5 billion years from now, they're going to look back at our star and it will look kind of like this too. But the next one is going to be a supernova remnant. So it is an exploded star. So this is a star that had a violent death, and it is called the Crab Nebula. There we go. And one of the reasons why we left it toward the end is that it's also kind of a low horizon object, but it's been on its way up as we've been doing the show. So it should be a little bit higher now. And here we go. And the Crab Nebula is in Taurus. The bull. So actually you can see the bull here. These are the bull's horns, and there's his face. The face of there's a red eye in Taurus the bull, and it's a star called Aldebaran. So that the red is at a red giant star. You can see it here. It's coming up on the list in our identifier. So Aldebaran is considered the red eye of Taurus the bull, which is near the constellation of Orion the Hunter, which is my favorite constellation. Another famous star in Orion, since we're talking about red giants, is Betelgeuse, which is the top left shoulder of Orion. And all last year, last fall, we thought that Orion might be doing, or that Betelgeuse might be doing some weird things, because all of a sudden it dipped in brightness by like half, and we had never seen the star do that before. And we know that Betelgeuse is near the end of its life. It could explode in the astronomically near future. Of course, that could be tomorrow or a million years from now, or maybe 100,000. But if it does explode, it will be bright enough to be visible in the sky, brighter than the full moon for probably 2 or 3 weeks at a time. And it would be bright, and it wouldn't fade away for almost an entire year before the star just vanished from the sky. Well, 1,000 years ago, that happened to another star in the sky, and it was the star that created this nebula, which is known as the Crab Nebula. So I'm going to reset our imager, and we'll start over, and hopefully we get some data out of this star.
Yeah, I remember about Betelgeuse last year because when I was observing the asterism, the winter hexagon, I kind of feel like it's not easy to observe Betelgeuse. Like normally, like during winter times, like when I go out to my balcony, like I kind of like recognize Betelgeuse the first. But for last year, like I find Rigel first before Betelgeuse. So that's how I recognize like something's weird it's going on.
Orion's just so pretty. I think out of the two famous, probably the most famous constellations, in the night sky, when you ask people to name one, they're either naming like, Big Dipper, which is technically an asterism, but whatever, we'll let that slide. And then you've got you have Orion, and they're just such prominent, beautiful constellations. All right. How long does it take to do a deep space shot like this? So, well, in this case, when we're exposing one of these images, we'll start, you can start getting clarity on the object within a few minutes. But if you look at most space photos that you'll see, regardless of the telescope, it could be on the Hubble Space Telescope or it could be on someone's personal telescope. Usually the exposure times are in the hours to either 5 to even dozens of hours in order to collect enough light from the object to make a picture. I've used this analogy in the past, but you can think of it like rain. So if you have a bucket outside in the rain, it will collect more and more water. Well, a telescope is like that, but just with droplets of light. We call those photons. And the larger your bucket, like our telescope 70 centimeters across, it's a pretty big scope, it's going to collect more rain more quickly. And so that's the advantage of having a wider telescope, is that you're going to collect more light in a faster period of time. All right, let's see if we have anything. We've got 6 frames stacked on the nebula, so let's see if we can see anything. Oh, I see a nebula in there.
Yep. Oh, I can see that too.
Yeah.
A very faint fuzzy patch.
It is there. So you can see the nebula starting to appear. It's kind of in here. And if you notice, sometimes Abby and I struggling to get the color and focus and stuff like that, it's because we have to drag these slider bars over, but we're doing it remotely, and there's a bit of a lag from the observatory, and so sometimes it doesn't actually catch that you're pulling anything, and so you're kind of like dragging it over and over and over. Okay, let's align some colors here a bit. So
Yeah, so just like just now, Matt saying, the nebula is located in the constellation Taurus, and there's this star you can use as reference, the Aldebaran. So if you're looking into a similar region with your binoculars, you'll be able to look at another star cluster. That's another beautiful binocular gem that's called the Hayat cluster. So it's around in a similar region. So there are a lot of one thing that I really like about the winter constellation is that there are a lot of beautiful gems, just like Matt mentioned about the Orion. There's Taurus. There are so many different types of nebulas and star clusters around the region. So I would say I really like the winter night sky.
oh yeah, the winter night sky is amazing. I've cheated here a little bit. I don't know if so over on the right side, I have it clipped off right now, so you can't. Oh, maybe you can't see that part. I don't know if you can or not. Anyways, but over on the side, I have some other tools that I have for processing, or that we both have for processing, and it's applying something called a dark frame and a flat frame. So these are processing tools that help the computer identify more of what's actually the picture you're looking at, and less of noise and just like physical junk, even like dust and dust bunnies that might be in the camera. And I don't know if I actually had those loaded up from the last time I changed, because every time we change modes on the camera, we have to reload them, and sometimes I might have actually forgotten last time. So I've noticed that some of the noise in the images might be the result of me forgetting to do that. So if that's the case, and all of a sudden this nebula shows up a lot clearer, then I apologize to Abby, because that might be why your dumbbell didn't show up as clearly as it probably should have. So let's see.
Oh, no worries.
There's a lot of things to juggle in these streams, everybody. I've got the chat feed going. I have 2 different monitors. I've got the streaming software. I've got, Abby and I are trying to Zoom to one another at the same time while doing this. These are tough. So we appreciate your patience when we don't get it perfect, because there's a lot of balls in the air for us to that we have to keep in the air to make these happen. Zeno was saying, I've tried imaging Rosette, but no, I have not imaged the Rosette Nebula, but I think somebody has. There's a lot of data that's floating around in the telescope that we should probably start processing. Okay, so let's try this again. Let's see what we got in here. How much time we got? Okay, we're starting to run out of time, so we gotta. Oh yeah, that's way cleaner. I am so sorry. I don't think I had our flats and darks applied, because that's a lot less noisy picture. But now we know. For those of you who are astrophotographers and astroprocess.
Oh, okay. I see a question for me, Abby.
Oh,
How did you get into astronomy? Okay, that's an interesting question. So I started at a very young age, but I didn't first start with astronomy. I first started with meteorology, because I find everything about the atmosphere very interesting. So I started learning about the weather system and geography when I was around 5 or 6, and I slowly transitioned into astronomy because I'm just ambitious. I just want to know more what's beyond the atmosphere. So I picked up a book about astronomy and I find it very interesting and I kind of felt in love with it. Then I just try to practice more and read more books and learn more about it. Yeah. How about you, Matt? Like,
How did
is there?
I? Yeah. Well, unlike I'm kind of I'm the one of the few who do the stream who are not actual scientists. So I always look up to you all with a lot of reverence because you're the actual scientists that do this kind of like this work. Whereas I'm an amateur astronomer, and so I got into it because my grandfather was really had a fondness for astronomy, and I was fortunate enough to grow up in a family that had a cottage on a lake that my grandfather built himself. It's a lake's called Shibanwan, and it's about 45 minutes outside of Thunder Bay, Ontario, where the skies were absolutely astonishing. And so my grandfather would point out the night sky. We had a little 60 millimeter telescope, and we would look at the rings of Saturn, and we looked at the stripes on Jupiter, and I fell in love with the sky doing that. And then I kind of got out of space for a number of years, and it wasn't until kind of like I would say back in 2011, it was the retirement of the space shuttle was one big thing that got me back into space because that was like, oh, that's that spaceship I always wanted to fly on one day, and it's being retired. And that kind of pulled me back into what was going on in space, and then buying a telescope, and then meeting up with I think through Howard a lot of the astronomy community here in town in Vancouver, and then thankfully the observatory itself has become such a pillar of a whole community of space people that now includes all of you. So thanks for hanging out, everyone. Okay.
Yeah, well,
Oh,
actually,
sorry, go
I'm
ahead.
also not. Well, actually, I'm also not an actual astronomer because I'm not studying physics and astronomy. So instead, I'm studying interaction design and interactive systems. So yeah, same as you. I'm just an amateur astronomer.
Yeah, it's
Yeah, sorry.
cool that as one of the fields of science, it probably has like one of the largest citizen science communities, which is pretty amazing. That we can all kind of do this stuff and have access to this kind of equipment now, which is amazing. Okay, I should probably talk about what we're looking at here. So this is a super-Rover remnant known as the Crab Nebula, and so it is located in Taurus the Bull. It was discovered in 1741, but it probably corresponds to a bright supernova that was recorded by Chinese astronomers in the year 1054. And so they had noted that there was a new star that was bright enough to be seen during the daytime. So think about that, like a star that was bright enough in the sky to be seen during the day. It's 6,500 light years away, so it even exploded way before we saw it in China for the first time. It's 11 light years across. And so here's an interesting comparison. The Dumbbell Nebula, the winds in the Dumbbell Nebula, are pushing outward at 31 kilometers per second. 31. The winds inside of the Crab Nebula are expanding at 1,500 kilometers per second. So this is a far more violent outburst of energy and material that's being spread out. Now, as a result of this, with supernova explosions create different kinds of objects. So planetary nebula will create what's called white dwarfs. So these are objects of the dead cores of stars that are left over at the end. They're quite dense, but they're nowhere near as dense as what's called neutron stars or pulsars, what's left over in the inside of supernova. Supernova will either create pulsars or even black holes. Pulsars are some of the most compact and crushed objects that you can find in the entire universe. And so basically one sugar cube of pulsar material with this name we sometimes given, it's more from sci-fi, but it's called neutronium, but would weigh as much as a mountain, like billions of tons of material squashed down into one sugar cube. It should give you basically inspiration the next time you go packing. So if you're packing a lot of stuff into a suitcase, just remember a star managed to crush a whole mountain into a sugar cube. So there's a lot of empty space in those clothes. Keep jumping on that suitcase. Now, one of the things we know about this pulsar inside of the nebula is that it spins, and that's the thing about pulsars. So they're about the size of a city. The one inside of the Crab Nebula is about 30 kilometers across. So it weighs as much as usually a few stars worth of material, worth of suns worth of material that are still crushed down inside. But it spins once every 33 milliseconds. So imagine that, something that weighs as much as a couple stars. It's 30 kilometers across, and it's spinning around thousands of times a second. It's amazing. The original star that created it was probably 8 to 10 times the mass of our sun. And there's a video of it. That's the coolest thing. So I'm going to show you a video. And this video is of the pulsar that is at the center of the Crab Nebula. And this is it being seen in both X-ray and I think infrared energy. And it spins around and moves fast enough. So this is the pulsar here at the center. This is the very heart of the nebula. These waves around the outside are created by the rotation of the pulsar. We call it pulsar wind. And so even though the Crab Nebula is a supernova remnant, it sometimes is also called a pulsar wind nebula. So if I run this time lapse, you can actually see the waves rippling outward from the pulsar inside the nebula. And hopefully you can see that with enough frame rate from over the stream to be able to see it. What does it look like? Oh yeah, you can. So look at that. So there we are zoomed in onto the center of the nebula. And these are the waves rippling outwards from that pulsar. And the pulsar at the center of the Crab Nebula is usually the brightest source of X-rays and gamma rays in our own night sky. So it's close enough to us to be able to create that much energy that we see it. It's also very useful. It turns out that when other objects move in front of the Crab Nebula, we can actually use the light from the pulsar, the energy from the pulsar, to map other objects. It's like having a beam that will pass through things that we can map. And so one of the things that we've used the Crab Nebula pulsar to do is actually map some of our own sun's atmosphere. Imagine that. That's so cool. So when our sun passed in front of Taurus one time, we were actually able to use the source of gamma rays from the pulsar to be able to map the atmosphere of our own sun, which is so cool. It's amazing that scientists think of this kind of stuff using all these tools to help us out. Now, Nikki had mentioned that there's actually a time lapse of the Crab Nebula expansion, and I didn't think to look that up, but I wonder if we can find it just really quickly. Oh, I think that's it there. Yeah. So this is another way to be able to see the change of the nebula over time. I wonder how great. Oh yeah, you can actually see it expanding here, and you see the ripples as well from the center, and you can see the outer edge is actually moving, and this is by year on the outside. So you can see it changing in shape in real time. We can actually see the dynamic of the winds moving outward, which is like absolutely astonishing. Okay, we're down to, we were going to look at a bunch of planets and stuff today. I don't know if we can fit those in still. We should do at least one. Abby, you want to do Uranus, so we should probably fit in Uranus, and then we'll make sure we jump to that last object before we end.
Okay. Sure. So let me go to Uranus. Yeah, just like you were mentioning about the pulsars, I find them really interesting. And I remember when I was learning about pulsar, I learned it about as the lighthouse analogy. Just like when you're going to the Maritimes part of the Canada, you see a lot of lighthouse. You can see a torch kind of spinning around. Then you can see a light beam like every other few seconds.
Right.
That's how I remember it.
Yeah, thank you. That's a really good point, and why it's called a pulsar is because it pulses with each of the rotations, like you said, just like a lighthouse. And so, but a lighthouse that's spinning very, very, very quickly. In fact, interesting about pulsars, back in the 60s when they were first discovered, we had no idea what they were. But the regular pulse in energy from them seems so regular, which it is, that it was theorized that it could actually be a signal from an alien civilization. Of course, we know now that that's not the case. But as a result, they were named, although kind of in an ironic sense, when we first found them in the sky, we labeled them LGM. Which stands for Little Green Men. And so one of the pulsars, the first pulsar we found in the sky was actually labeled LGM1 because we thought, well, maybe this is actually a signal from an extraterrestrial civilization. We know that is not the case. Abby, did you want to go did you want to turn off live stack mode so that we could see the planet sort of in live in real time?
Okay. So here it is.
I think that's
Do
yeah.
you want to zoom in?
Yeah, you can if you
Yeah.
want. Yeah.
You can take over.
Okay, sure.
Yeah.
Okay.
And
And then do you want to talk a little bit about? I know you had some interesting facts on Uranus. You wanted to.
yeah. So let's wait.
Let's see if we can. I'll just bring it more into view. And Uranus is pretty far away, so it's gonna look a little fuzzy. Whenever I talk about this planet with my with the young elementary school group, you can always get the laughter, as you can imagine. So there it is, the
Yeah.
fuzzy ball of Uranus.
So yeah, so we're now looking at Uranus. So as you can see, like if you're looking at actual space image, it shows up as bluish green color. That's because Uranus it's made up of methane. It's another type of gas. So something different about Uranus is that they're called ice giants instead of gas giants. So they're a little bit different from the planets we have seen earlier in the summer, Jupiter and Saturn. So why are they called ice giants? This is because these type of planets they consist of mostly like water, rocks, methane, and ammonia instead of hydrogen and helium. So that's why they are not considered as gas giant. So Uranus takes 84 years to revolve around the sun. So and it takes 17 hours like to revolve itself once. So, but however, Uranus has a very different axis. Like it's very tilted and it's close to 90 degrees. So you can think of it as you can think like Uranus, it's kind of like rotating, lying down. So that would cause very extreme weather and season and daylight condition. So imagine like if you're living on a planet that you have like 40 years of daytime and 40 years of nighttime. I really couldn't imagine like how life or how the entire ecosystem would be. Yeah, so here's an image like that I drew earlier. So depicting how it's looking like. So as you can see in here, this orange axis is the axis of Uranus. So it's very tilted. And the straight line here is the equator of the Uranus. So you can see when it's facing the sun, this side like it's facing the sun it's during daytime. However, it's gonna be daytime for like over 40 years because of its axis. So no matter how fast or how slow it's spinning itself, you still have very extreme weather condition just because of its axis. So it's also like Earth. So Earth has some very mild axis. It's like 23 degree. So that's why we have 4 different seasons, just perfect. If we live on Jupiter, so Jupiter does not have a really tilted axis. It's only 3 degrees, so it's almost straight up. So if we live in Jupiter, we would actually have no seasons at all. Yeah. Matthew, how would you imagine like your life if you spend 40 years in darkness and 40 years in daylight?
I would get a lot of astronomy done.
Oh yeah, I agree with that, but
I could
also
spend
thinking
40 years imaging and then 40 years post-processing.
yeah, I agree with that. Like that would be cool, like 40 years studying astronomy. But also 40 years of like minus 200 degrees Celsius. That wouldn't be nice. So,
Cool.
yeah. So, do you want to move to our final target, the grand final, the grand finale?
Okay, so we have one target that's a favorite of all of us, and now it's up around this time of year. We can finally see it, and it is the Great Orion Nebula. And we did some tests on Orion earlier in the month, actually, because we were up super, super late, much later than the stream normally goes. But now it's up early enough that we can share it with all of you. So hopefully this works out. It's still quite low in the atmosphere, but I think it should be okay. So let's go back to stack mode. And this one is so bright, it shines through so much that it should be a very clean picture. But let's not get our hopes up too much. But last time we imaged it, it turned out really good. Okay, let's reset. load our darks and stuff again. All right, turn on the live stack. Let's clear this out. All right, let's give it a try. All right, how high is Orion now? It's definitely high enough. Okay. All right, here we go. Let's see how it looks. Oh, already amazing.
Yeah, it's coming through.
See, that's beautiful. So, some cool things about the Orion Nebula. Abby, what do we know about Orion?
Well, we know like it's a very bright nebula, so it can be actually seen with naked eye if you're in great condition. I remember looking at the Orion Nebula last year using my binoculars. It's absolutely beautiful, and I really love looking into it because although like it only shows up as a gray fuzzy patch in your binoculars, but something special is that like this is the nebula that it's so prominent that it shows up so well in your binoculars. So yeah, it's so rewarding like the second that you look into your binoculars. That's something I like about it.
Yeah. So we like what's amazing if right away you can see just how bright and prominent the nebula is because in the past when we've been everything else that we've had to image, everything that also we've been imaging, we got to like process it and stuff like immediately. We're always stretching and pulling our histograms, but this like it just shows up right away. We don't have to do anything and it's already right in the field of view. So just to show you where we're pointing, because you can actually see the Orion Nebula with the naked eye. And I'll show you where it is. So when you zoom in on, if we zoom in here on Orion, and there you go. So you have that, the classic 3 stars of Orion's belt. And then you have 3 stars that are, that kind of come down from Orion's belt. This is supposed to be Orion's sword scabbard. So this is kind of like where he keeps his sword. Well, the center star of the 3 coming down from the 3 of the belt, the center one, it looks like 1 star, but it's actually the light of the entire nebula. So when you see this with your eye, you're actually literally looking at a whole nebula of stars. There's probably about 2,000 stars that are being born in the Orion Nebula. We call it a stellar nursery. And it's literally like, you know, a birthplace of brand new stars. And it's one of the closest star forming regions. I think, actually, if I'm right, I think it's the closest star forming region to Earth where baby stars are being born. The light itself, which we'll bring up now. As soon as my mouse knows that I'm moving something. There we go. Hang on. Yeah. Ooh. Go mouse. There we go. Okay.
Yeah, so in this image, like you can see there's 4 really bright stars in there. So that is called the Great Trapezoid. So it happens that the 4 stars in there are giving out most of the brightness of the whole nebula. So yeah, that's something really interesting to me.
Yeah, so like although there are, yeah, you're right. I mean, so while there's thousands of stars that are in the nebula, it's really this like this center cluster that is giving off most of the light of it. And so it's like the light of those center stars is so bright that they are rippling through the whole rest of the nebula and giving it its light. Look at, we have so much here that it's hard for me to actually get it without clipping it down too much. So someone asked if this is stretched. So yeah, I haven't even really stretched it at all right now. I've just brought like the black level down and stuff. But yeah, I have not stretched this picture. This is just how it looks. I'm gonna bring the mids back. Here we go. Yeah, it's amazing. You can see all the filaments in the nebula and everything. This is still, this, and then this looks amazing. It'll only get sharper as we go throughout the year as well, because it'll get higher and higher on the horizon, and we'll be able to see it through less and less air as it gets brighter and brighter. But yeah, this is one of the most beautiful images, or beautiful targets, that we can see in the night sky. The light of all the nebula. And we're about ready to wrap up. Before I go, actually, so Orion is one of the other objects that we have imaged with our primary camera on the telescope. So remember, this is our little webcam that we use to take images. But we actually have a fully processed image of Orion from our primary camera, and I will show it to you if we could get it to actually open. There we go. And here it is. So this is the Orion Nebula through our primary camera on the telescope. This is a series of, with the camera that we're using right now at the observatory, we're doing 20-second individual exposures. The one we did to put this one together is 1 second. They're just 1 second exposures each, because Orion is so bright, even to our primary camera, that each individual exposure is only 1 second long. And it's added, this is an added total, I think, of almost 1,000 1 second images, and that I put together over, I think, two nights. This is one of my first objects that I tried imaging, because as amazing as it looks, Orion's pretty forgiving for a first-time photographer, and having access to the equipment I do. So don't give me too much credit, because it's one of the easiest things to image in the sky, and I have access to a giant telescope. But so we put it together and then did some post-processing on it, and then you get this. And one of the cool things about it is that because the resolution on the image is so high, you can zoom in, and so the field of view that we're getting on the tiny telescope right now is kind of like this, and you're looking again at, Abby was saying, the trapezium cluster, these stars that are in the center that are essentially illuminating the entire nebula. And because most of the nebula is made out of the raw material that stars use to form themselves, so hydrogen and helium, it's basically red. It shows up primarily red when it's exposed to energy from the rest of the stars. It's basically glowing like a fluorescent light bulb. Essentially, it's just gas that's being exposed to energy, just like a fluorescent light bulb works. And then there it is. Yeah. So I think what time we're at? We're at 9:33. Here I was earlier thinking that we're going to run out of time, and we actually had to skip a bunch of things, mainly planets. But I think it was worth it, because we've seen some of these planets before, but this was the first time we got to actually introduce Orion Nebula for our virtual stream. So we're very excited that it was high enough on the horizon to be able to do that.
Yeah. I love the image. Like, that's absolutely beautiful.
Isn't that cool? It's so good. Yeah, and it's so it's so noise free because it's so bright. So it's one of the things that will show up and very clearly throughout the next couple streams, I'm sure. So if you're around for tonight and someone wasn't here, tell them, hey, you got to come to the next one, because they're looking at the Orion Nebula these days, and it's beautiful.
Yeah. So I guess this brings us to the end.
Yeah.
So thank you everyone for joining us, walking you through the star. We thank our moderators, Cal, Sina, and Susanna. And also thank you, Matt.
Yeah, I think I saw Ken in here earlier too. Did I see Ken as well? Ken, I think you're here too, maybe hanging out. So thanks for joining in, and thank you everyone for joining. This is how many people we have in here? Over 100. That's so good. That's higher than a lot of them recently. So thanks so much. And Abby, thank you too for helping me put all this together today and putting together a list of targets and testing things with me, and I appreciate that. So thanks. It's been nice to do these co-hosts with people, because I think it there's less time for the audience just listening to us in silence while we try to fiddle around with processing.
Yeah. So keep looking up. We have great nights.
Yeah, and we'll see you on soon. We'll advertise the next one as soon as it's ready. Have a good night.